All right, let's begin. This is just a quick reminder of what we learned about double slit experiment. And actually it is here that you have double slit that are separated by a certain distance, 1.2. I don't know if you've already done the lab involving double slit, but this would be the experiment. And you shine light on it with a particular wavelength. And what you then look and find is that there are these fringes. There's a bright fringe in the middle because the two wavelengths of the lights that go through this slit and the light that goes through this slit, they have the same, they are in phase because they came from a coherent source, right? They came from a coherent source and therefore they will now be bright. But when it is over here, the ray that came from this slit is now, the path that this slit had to take is longer than the path of the ray that came from this slit and differed by half a wavelength. And if it differs by half a wavelength, they will be 180 degrees out of phase. When you are up, I'm down. When you combine, it becomes dark. Oh no, over here, it will be dark in between. This one is to look for another place where the path length difference is integral multiple of the wavelength. So then this is bright, but it would be bright, dark, bright, dark, bright. And they just want to know, well, what is the distance? Find the distance on the screen. Oh, this distance. Find the distance on the screen. That's the kind of thing that your lab instructor will say, yes, you measure that. And what you do is you then use the basic formula. Sine theta is m lambda over d, where lambda is the particular wavelength of the light. D is the distance between the two slits, and theta is the angle. And if they tell you m is 3, you substitute lambda is, their given is 664 nanometers, and the angle, therefore you work it out, or the book has already worked it out for you. It is about 1 degree. And the y distance, therefore, is trigonometry, is L, is the y is L tangent of theta. And they already told you it is, the screen is 2.75 meters away, and you discover that indeed this third bright fringe is 4.5 centimeters. And then there was this conceptual question which we already ended last time by saying that the white light, all the different wavelengths of blue light, green light, red light, they all are bright. Therefore, in the middle is white. But when you now look for one of the fringes where you see some color, what happens is you will see a spread of colors, red, orange, blue, green, and so on. And the question was, why is red farther out? Well, that's because the basic formula is here. Since red wavelength is longer than green wavelength, so theta would be bigger. That's why it would be further out. All right, so we ended there. Any questions about this Young's double slit experiment? Okay, all right. So now I know many of you have been very concerned about your test 2. I don't have the grades back from the grader. I wish I could talk to him and say, hey, fellow, please, But anyway, he keeps saying, first he said that his computer conked out. So he had to have somebody repair it. And now he says he's striving, striving, striving to have the test graded by the end of today. Well, I guess for him, this is not yet the end of today. Anyway, if he does not finish it by tonight, I will grade all of your things for tomorrow. I mean, in tomorrow, right? But in order to comfort you, I'm going to show you the solutions. Oh, and the other question is your next exam after Thanksgiving? No, it's before Thanksgiving. November 22nd is the next test. The reason is the final is December 15th, and it's very soon after Thanksgiving. So we cannot put this one off to after Thanksgiving, because then there is no time for the rest of the semester, okay? And the final is cumulative, and the final will have double the number of questions, and it will cover, basically everything, except that it would be from the perspective of we having learned more about stuff. But it would be cumulative, and therefore it will again cover various things. Okay? So now, in order to sort of like just let you at least have some peace, I will now quickly go over the test. Now, can you see it? I don't have it magnified. But the question which I think many people had difficulty with is this. What do you call it now? I think medical term, there's a term for it. They want to measure the blood flow. They want to, or you as a biomedical, you want to measure the blood flow. You want to see whether my carotid, the blood is flowing with the expected normal healthy flow rate, or is there some blockage somewhere so that the velocity now is higher and so on. So you want to measure the blood flow by a non-invasive procedure. And the way you do it is to make use of electromagnetic induced, EMF. And so what you now say is, well, blood is like water, is a conductor. So you have blood flowing. So it is like a conductor. And now you put in a magnetic field. You, namely the technician, because you put somebody through, and the technician applies a certain magnetic field, and this magnetic field is into the board, right? My eyesight is not that good. Or is it out of the board? Is this into or out of the board? I don't know. You have to, my eyesight is not that good. Anyway, you now say, I have now a current flowing, and it is now flowing this way. And I now know that because it is flowing through, these charges are flowing through, there is a magnetic field on it. Then there is a induced motional EMF. There's an induced EMF, and you now want to know what is the voltage across. The induced EMF is the voltage across. You would like to know what is the induced EMF across. And the formula for the I keep wanting to say emotional. Am I too emotional? Huh? Yeah, nobody is emotional. The motional EMF, right? And that is, the formula is VB times D, where D is the gap. And in this case here, this blood vessel is a vessel of a certain diameter. So that is D. That actually is the gap. And now, when you now have your instrument will now measure the current that flows. Therefore, you know what is the voltage across this, and the magnitude. They want to know what's the magnitude of the voltage that is measured with the electrodes in the drawing. And you just use VBD. And this is the multiple answer choice. VBD times 10⁻³ and so on is different ways of confusing you. But if you know your basic formula, then you say, this is the formula. All right. So that is this thing about trying to measure the blood flow. And the other one is you have a conducting bar. It moves to the left at constant velocity through some magnetic field. And they don't show you whether it is out of the board or into the board. They just simply say, as this rod is moving through, there is now an induced current. But they have measured the induced current to be, in fact, counterclockwise. And the question is, which way is the magnetic field? Well, then you have to remember this guy, Lenz law. You remember Lenz law? Well, the Lenz law says it will be to oppose any change in the flux with Faraday, Faraday and Lenz law. And now what happens is this thing, this current here, you have to use your right-hand rule. When you use the right-hand rule, you will find that the magnetic field due to this current is out of the board. Do you have your right hand? Do you know how to curl your right hand? With your thumb in the direction of the current. So this is therefore the magnetic field is coming out of the board. And now what happens is, because this rod is moving this way, it's decreasing your flux. Because flux through the loop is whatever's the magnetic field times the area. But your area is decreasing. So the magnetic flux through the loop is decreasing, and the induced current says, oh, hurry, I got to make up for it. I got to make up for it. I got to help oppose the change. The change is the magnetic flux is decreasing. I help. How do I help? The induced current flows this way. All right. Do you now get the concept? It's a very simple concept. It's just that you have to grasp the key point about Faraday's law and about Lenz's law, which is that it is to oppose. They don't want anything to be changed. And since you're moving your rod this way, you're decreasing the flux through my loop. And I really am hurt because you're decreasing it. So I will now have my induced current to make up for it. So therefore, this says that the thing is coming out of the board or coming out of the page. Now, this is another question which involves a loop again, but you already have a current flowing this way, and the loop was just there. But then it says you did something. Suddenly, the wire is moved closer to the loop. All of a sudden, I don't know why, maybe your sibling or your kid started to play around with my wire, and you move this closer. And then what you need to remember is this thing about Mps Law, right? That if I have a current, then there will be a magnetic field through this current, and the strength of the magnetic field is stronger when it is close to the wire, but it is weaker as it goes further and further away. You remember, that's from the Mps Law, right? And what happens, therefore, is when your sibling or when your whatever kid pushes the wire close, you are in, ooh, what did I do? When you push it closer to the loop, the magnetic field passing through the loop is now increased. Why? Because you're getting closer to the wire. The magnetic field is due to this wire. You move the wire close to me, the magnetic field is now increased. And so now Lenz's law says, I must now have an induced current. And it must be to oppose it. Since you have this magnetic field into the board, you see it? You have to use your right hand, your finger, right hand rule. The thumb is in the direction of this wire, and the magnetic field is into the board. But now you're increasing it. So what does the induced current loop, the induced current in the loop, what will it do? It will now oppose you. So the induced current will now flow counterclockwise, because then the magnetic field would be opposite, to oppose the change. All right, so the answer is it will be counterclockwise. Okay, now you go to the next one. You now have this charge moving with velocity v. It is charge q, whatever q is. You just have to be careful. This is microcoulomb. So whatever is this charge coming this way, in a region where you have magnetic field and electric field both upward. And I have put down the x direction, y direction, and z direction just to be very precise. Okay. And then the question is, what is the force acting on this poor guy? Well, that you remember is Lorenz Force, right? Lorentz, a very famous name, a Dutch physicist. Well, he is a very well-known name, the Lorenz Force. And the Lorenz Force is where you say, if there's a electric field, I have, of course, the Coulomb force, Q times E, E being the electric field. But because now there's a magnetic field, there is plus Q V cross B. And you have to know your vector product. Whatever is V and whichever is B, you got to have V cross B. And this problem here is to now ask, what is the actual magnitude of the actual physical force acting on this poor charge, because it is subject to electric field and it's subject to magnetic field? Well, that's easy. You know, due to the electric field, it's just Q times E. But due to magnetic field, oh, you have to remember from one of your PowerPoint somewhere, right? That it is Q V vector cross B vector. And when you take V cross B, you will know that V cross B is out of the board. And the electric force is in the Z direction. Do you see what I'm doing here? The electric field will give you a force which is in the Z direction, because this guy is positive charge. And V cross B is out of the board. Therefore, if you want to know the magnitude, you just simply take the Z component force plus the Y component force, and you take the square root, Pythagorean theorem. And the only thing you have to be sort of very careful about is that this is microcoulomb and this is so many kilovolts. So when you have microcoulomb and kilovolts, it ends up with 10 to the minus 3. And the way the book has the velocity and the Tesla, again, the velocity is measured in units of 10 to the 6 meter per second, and the magnetic field is in 10 to the minus 3. Therefore, this also is 10 to the minus 3. Therefore, the answer is just this. And then the next three questions are being more fussy and say, which direction is the force? What is the force in the y direction? In y direction, it cannot be due to the electric field, because the electric field would have given you in the z direction. So the force in the y direction is all due to the Lorenz force, V cross B. But we already said it is out of the board. Therefore, since the orientation of y is into the board, it is negative QVB 10 to the minus 3. All right. And for what is the force in the, what is this now? This is in the x component. Well, in the x component, there is no force. Why? Because the electric force is in the z and the magnetic force is in the negative y. There is no force in the x direction, so that's 0. And what is the z component? Oh, that's very easy. It's totally in the z direction, QE times 10 minus 3. All right, so you can see it is not that difficult. Okay, so the next one is a more, maybe you can call it fuzzy one. You have electromagnetic wave, and it is coming incident on a plane of your paper. So the electromagnetic wave is coming down and the sheet of paper is down here. And what we have is, we're told at time t equals 0, the wave strikes your paper at normal incidence. The magnetic field vector at point O over here points in the negative y direction. Okay, so it's coming down and has a certain magnitude, 10 to the minus 8 Tesla. The frequency of the wave is 10 to the 16 hertz. The velocity of light in vacuum is 3 times 10 to the 8. Oh, this one is 10 to the minus 8. This one is 10 to the 8. And the question is, what is the magnitude of the associated electric field? And then you have to remember in your PowerPoint or in your Wiley Plus book that in vacuum, the electric and magnetic field, they are coordinated. When the electric field is maximum, magnetic field is maximum. When the electric field is minimum, B field is minimum. But they are always proportional to each other when they're going through the vacuum. And the proportionality is C, the velocity of light in vacuum, the velocity of the electromagnetic wave in vacuum. And so you say, if you now tell me what is B and you want to ask what is E in these engineering units, it's very easy. It's just C times B. But C, they already told us, is 3 times 10 to the 8, and your B is 10 to the minus 8 Tesla. Therefore, E is 3B. All right, so that's an easy thing if you know what they are asking for. And now they say, which direction is it? Well, you have to remember that when an electromagnetic wave is propagating, the direction of the propagation is E cross B. You always have to remember it's the direction of propagation, right? My thumb is showing the propagation, then it is E cross B. So since B is downward, what you want is the thumb to be downward, and therefore I have to get my B field is downward, E cross B. Which way do I have to do? E cross. If it is this way, the wave is propagating upward, but it is downward, so it is I don't know how to get my z-axis is XYZ is into, this is downward is negative y, x is this way, z is that way, and what I want is my, am I doing it right? Yeah, the propagation direction of the electric field. I have E cross B, so it is coming down, points in the direction of, what is this now? Positive X direction. Yeah, X cross B. Yes, X cross B. If I have my fingers right, I have my X. Well, this is my board. X cross B is this way. So it is, I don't know which one is the paper now. Oh, the paper is in the negative Z direction. Okay, all right. So it is coming down, and the paper is in the negative Z direction into the board. So when I have my electric field this way and my magnetic field this way, the electromagnetic wave, the light or the wave is going towards the paper, and the paper is in the negative Z direction. So that's why it is E points in the positive X direction. All right. And now what's the next question they ask? What's the direction of polarization? Well, polarization is, as far as the E field is concerned, which way is the E field oscillating? Well, it's in the X direction. So the polarization is in the X direction. And then the last two questions has to do with this inductance, mutual inductance. Now, if you look back into your PowerPoint or look back into your Valley Plus book or ebook, the inductance is measured in terms of the induced electromagnetic field, EMF, is negative, and it is the mutual inductance, and then times the rate of change of the current, delta I over delta T. Here they are telling you I has changed all of a sudden to 0 in a small time. Therefore, delta I over delta T is basically the whatever is the current over that time interval. And the mutual inductance, M, is the actual induced EMF. The induced EMF is the mutual inductance delta I over delta T. So you just invert it to find out what is the mutual inductance, and that is the formula. And then for the transformer, oh, it's very easy. The voltage step up or step down depends on the number of turns. And what they told you is that the primary coil has a small number of turns and the secondary coil has a bigger number of turns. So what is the resultant voltage? Well, it depends on how much bigger number of turns it is. It's the ratio of the number of turns times whatever is your original voltage. So this is the calculator formula. All right. Oh, even there. Oh, yeah. There's also on the light. Now, this one is interesting because it has practical application. I mean, this is going over chapter 26, I think. Yes. Is it 26? I get my numbers all mixed up. It is on this thing about reflections. And what you have here is, huh? Oh, 25? Yeah, is it? Are you sure it's 25? I don't know. I get it all mixed up between 24, 25, 26, 27, 28. All right, my friend says it's 25. But this is important because we use it all the time. You may not realize it. We use it all the time. You have a convex, no, this one is a concave mirror. And I got the answer mark wrong, even though I got the right answer. I don't know. That's why the grader has to go over it. So, because Blackboard is so fussy, if you didn't give it exactly the number of decimal places that it asks for, it will say you are wrong. You get 0. But that's where my grader has to now patiently look at each one and look at it. All right. Well, let's talk about this. This is an important issue because you want to have your sun's heat solar heat, solar energy. You want to now focus the solar energy onto your application that you have in mind. And what they are talking about is they want to collect the solar heat for what? Maybe to heat up the food or to heat up something. So they want to collect. And what they do then is they have a concave mirror of a certain dimension, which we call D. And now they want to collect all of this solar ray, solar energy, onto this focal point, and that's where they put their whatever thing that needs to be heated up. Well, you then have to now ask, how much is the heat that has been collected? The heat that's been collected, first of all, one thing which this question does not quite answer, but the technician, when they install it, will have to, is that this concave mirror has to be focused on the sun all through the day. So the sun rises and the sun sets. So this concave mirror cannot be just cannot be on the roof just by itself. It's got to have something that can track the sun, right? And for a given day, how many hours can you have? Well, they say it is what? 12 hours. In Phoenix, Arizona, indeed, on a sunny day, you can fully focus on the sun and follow it for 12 hours. And what you now are doing is you are focusing it onto this focal point, and you now want to know how much energy was collected. Well, of course, the energy that's collected is all of the solar energy coming in, and we are told is about 1,000 watt per meter squared in Arizona. So if it is 1,000 watt per meter squared, I know my area here because I know my diameter here. Therefore, I know how much has been the heat that has been collected, focused on this point, and I know it was for 12 hours and knew it in terms of kilowatt hour, 12 hours per day in a month, 30-day month. You can then figure out that it is 90 pi d squared. All right. When you put in the numbers, 1,000 watt and so on. And now what was the question? The question, all right, so that takes care of this part, right? And now this one is basically collecting all of what we have learned from this mirror. And now they have a concave mirror. And now the concave mirror is in front of you, and you are sitting there. And now when you are far away from this concave mirror, what do you see? Do you see a upward image or inverted image? Well, you have to go through your slides, right? And then you'll find that when you are far away, the image is inverted and real. The image is inverted and real, okay? But now, as you come closer and closer, that means that you as an object become closer to the mirror. Well, because that's what the instructor did. The instructor brought the concave mirror closer and closer to you. So when you get closer and closer, then all of a sudden, you now have a virtual image, and the virtual image is now enlarged. So you see yourself bigger. That's what this whatever this ABC this is the correct choice of the answer. Okay. Somebody had a complaint. How do you give partial credit? Do you say this gets 10 points, this gets 5 points, this gets 3 points? I don't know how to give a partial credit. Either you got it right or you got it wrong. No, that's what I'm saying. How do you now tell the grader and say, when you see this, oh, be kind to them. Oh, now if they chose, this one, maybe they are also right. I don't know how to ask. I don't know how to instruct the grader on that. And in fact, my choice is not to. You either got it right or wrong.
No, Professor, they're not saying.
Yes.
Yes,
So what are they saying?
we chose the correct answer, but it's still marked wrong for some of us. That's what we are saying. We're
Oh,
not asking you to provide partial.
oh, okay. Now that the grader can see because I showed the grader exactly what I show you here. So he knows that this is the correct answer. And if he sees that the blackboard for some reason doesn't like you, because you abused blackboard so many times before, and they say, well, I will mark you wrong. I don't know. I don't know why blackboard would do it, but the grader, he would know. I mean, when he's doing it with my solution here, he would know. Okay, and he would spot it rather. Okay, all right. Now I want to come back to thin film interference because that is a very important topic which we already did, but I want to summarize it again because, by the way, the fact that we already had it on test 2 for the final, it does not mean that therefore we will never ask any other question involving thin film interference. So I'm just telling you, the final, it will be cumulative, and therefore there may be other aspects of this thin film interference that can be asked again. All right. So please do not say, oh no, you already tested us in test 2, therefore no such questions involving anything having to do with thin film interference. There is no such deal. Okay. All right. Now, so here is the thing about the thin film interference. Because what happens is when you have this ray, it certainly got reflected. But when this ray got reflected, it got reflected by a denser medium. And when it's reflected by a denser medium, the electromagnetic wave has this very strange thing that it becomes 180 degrees out of phase. It becomes 180 degrees out of phase. But now when this ray goes into a denser medium and then it gets reflected off a less dense medium, because gasoline, the index of refraction is 1.4, water is only 1.3, but when it's reflected off an interface, a phase where this side is less dense, then there is no 180-degree phase change. It just goes whatever was your original phase. And therefore, when this thing comes back out, there is this new strange thing that can happen. This was integral multiple, so that it was still in phase. Whatever your phase was, it was still in phase. But when it came out, instead of being constructive interference, it now becomes destructive because this one was 180 degrees out of phase. So what came out when I have 1 and 2, 1 came from this reflected phase, and this one came from this side, that they will now be destructive. Well, this is just to remind ourselves that the wavelength of the light inside the film is whatever it was outside divided by n. And this is the rule that when light is reflected off a denser medium, there is a 180 degree out of phase, whereas if it is from a smaller index of refraction, then there is no phase change. And when we now calculate for this one, we already did that, but we can quickly retrace it. If I have wavelength of the incident, and the particular problem is blue light. If I have blue light incident, then when it was reflected here, it underwent 180 degrees phase change. But this blue light came in here. It now will have a different wavelength because it is now in a film with a denser, index of refraction. But now this would be reflected with no phase change. Therefore, this wave, which is the light, when it comes back out, it would be whatever was the phase here. And when this is integral multiple of the wavelength, so that when it has gone through 2t, because the thickness of the film is t, when it went through 2t, and this 2t is integral multiple of the wavelength, this wavelength being inside the film, then there is destructive. Why is that destructive? Because this guy had a 180-degree change of phase. All right, and this now says, but T we have said is m lambda film over 2, and therefore the thickness for the blue light to be blocked out, for the blue light to be removed because of the destructive interference, the thickness of the film has to be m being the least such, being 1. It can be 3, it can be 5, but it is for the least, right? Then it is 469, the original wavelength of the blue light, divided by the index of refraction of this gasoline. And they then say, oh, the thickness of this film is very thin. It's 168 nanometers. All right. Are you comfortable with that? What was it now? Okay, somebody already answered the question. This is a small angle. You are close to the, for small angle of incidence. When you're close to it, this one got bent closer, so the path length is the same as the thickness, because the difference between this and t is very small for small angle. Okay, the normal is normal to this is here. This is the normal. Okay, you see it? This is the normal, and the angle is small because you are looking above it. Okay, all right. Now this is a just a good, let's say, daily life experience, right? Here you have some kids that are actually blowing up a big sort of a balloon or something, but the balloon is has oil on it, and then when it is now, when they play with it, oh, there are all kinds of colors. You have blue, and you have some orange and so on. And the question is, under natural conditions, thin films like gasoline on water, or like the soap bubble in the figure, although I have never seen a soap bubble this big. Have you seen a soap bubble this big?
No.
Oh, you have? I guess it takes a certain skill to have a soap bubble that is big. I've seen people blow soap bubble, but they're also small. But it does take a certain skill, Yeah. Oh, not soap bubble? I don't know. What they say, a soap bubble in the figure. Whatever. I mean, there are things that you play with, and sometimes you can have a big bubble, but with a film of, some soap or gasoline. Hopefully it's not gasoline, but it's some kind of soap. And now they say it has a multicolored appearance that often changes while you're watching them. Why are such films multicolored, and why do they change with time? Now, that's a good question. Why are they multicolored? Well, that's because when you are seeing it, you're seeing the soap bubble at different angles, right? This part of the soap bubble, are the film where the light kind of came out at this angle to me, whereas this part of it came at a different angle. So the light where it was destructive interference occurred for different wavelengths. So from this particular wavelength, it was the blue light that got killed, so that only green light came. Whereas from this part of this bubble, it is now the green light that was, destructively interfered, and only blue light came. So I see blue here, I see green there. You get what we are talking about? Because in the real light, what we did earlier was sort of very simple, only flat, absolutely flat, and then for small angles. This is real life, where the soap bubble, in fact, is not exactly a spherical. It is whatever funny shape it is. And over time, the soap bubble is expanding or contracting. So it is actually very lively. It is not like what we had in the previous slide. It is lively. Therefore, what was let's say blue here now became a nice green, or it became yellow and so on. So it is a shimmering thing, right? Yeah, there is a certain order, but the thing that the order gets all messed up. Why? Because my soap bubble is alive. Whereas the double slit experiment, oh, the double slit is not alive, you know that? The double slit is, I wouldn't want to use the word dead. Is there a better word than to say that the double slit is dead? The double slit is fixed. It does not, doesn't do anything. And so I see we had the previous slide where it was, red and then blue, green, within the first bright fringe. So the order was still the rainbow order, but here it is live. And therefore, what was blue that was destructively interfered is now green, because it is, changing. And the other thing is, in a soap bubble or in whatever bubble you have, the temperature is not exactly the same. There are small variations in temperature. Yeah, because especially for a big bubble like this, it's a variation in the temperature. And the density of air changes with the temperature. Therefore, the lambda of the film also changes with your, particular temperature. That's why it's very lively, and you can now just enjoy it. And even the engineers will say, oh, please don't give me that problem to figure out what exactly it is at this instant in time, at this spot in the bubble. Even the engineers will complain, why don't you just sit back and relax and enjoy it? Yeah. But at least to understand that there is a underlying reason for the change in the color. Okay, is that comfortable? Is that okay? All right, I just see one yes, but I guess if I see two yes, I can go on. All right, thank you. At least there are some more, right? And now we come to a subject which is the air wedge. And I want to now take another example. The previous example was what you call the thin film interference. Now, what you have are, let's say, a wedge formed from two glass plates, and then you shine light on it. Well, they show a light source. You shine light on it, and you now want to play with or figure out what this strange rule about the extra 180-degree phase change when it is being reflected off a dense medium. They should have a name for that rule, but they don't have a name for that rule. They just simply say it is a rule. But this air wedge is a sort of an application of that rule. And I don't know if upstairs on Marshak they have this, they ask you to do this, but it's an interesting one nonetheless. So let us try to apply the rule of the thin film interference to this air wedge, especially since the book covers it. And so now we want to say, I have an air wedge. Why is it called an air wedge? It's air that is trapped between two glass plates. And you now want to know, is there anything funny happening when I shine light on it? And there will be one beam that got reflected and another beam which get refracted out and then get reflected again. Okay, so you have now one beam that in fact was reflected over here, came back out, and then another one that went through, and you notice when it went through, it gets bent away from the normal because this is dense. Air is a very light medium, so it got bent away, and then it got reflected over here by this glass, and it came back through the glass. And now the question is beam 1 and beam 2, are they going to have some interference? And of course, you will say yes, you would expect some interference. By now, you're expert that there should be some interference. And what they want to now figure out is what's the rule for this interference between this and this. And it's all based on the basic concept of thin film interference. So we will say, okay, I now have number 1 wave. It actually came to be reflected off this end of this surface where it is dense medium and light medium. And when it's reflected off a dense medium and light medium, there is no extra unexpected 180-degree phase change. All right, so it just got reflected. Whatever was the phase when it came here, you get reflected. But now the refracted ray that got bent out, then went into the air. It's no longer in the glass, went in the air, and now it got reflected off the other glass. So it got reflected off a dense medium. And then you say, whoa, there is a 180-degree half wavelength phase change here upon reflection. I didn't have my arrow, that I should have arrow a little bit tilted down, yeah? You don't mind, right? That the reflection occurs here, but not up there. It's I should have tilted it a little bit more, but with PowerPoint, sometimes not so easy to tilt it a little bit more. But anyway, you got the point here, that when it got reflected by this glass over here, there would now be an unusual, according to the rule, an extra 180-degree. And then it went here and went there. There's no more 180-degree thing. It just went through. Okay. And so now we say, I add in this, the book didn't have this called T. I add in this T because that's the thickness at the point where we're talking about this reflection. So there is now an extra 2T because the angles here are all very small, and it's actually roughly 2T. When it went down this way and back up, it is roughly 2T. it is exaggerated here in this diagram, but it's actually about 2t. And this is the extra distance traveled by wave 2. Extra distance compared with wave 1, because wave 1 had to go through the upper glass plate. Wave 2 also had to go through upper glass plate. So we don't need to figure out what is the difference. Let the engineers, more precisely figure it out, but we just want to know approximately. Approximately, this path length is the same as this path length. This path length is the same as this path length, and this path length and this path length and t are all roughly the same. So 2t is the extra distance traveled by wave 2. But there is wave 2 has an extra 180-degree phase change. All right? Therefore, condition for constructive interference. If I now want to know, I want there to be constructive interference. What is the condition? The condition is 2t must be m plus a half. Because if this itself is m plus a half, then when you add to it this extra half, then it becomes in phase with 1. You follow that? This is the most important point of this whole exercise here, of this example. You went as 2t, but when you went 2t, it was m plus a half. In other words, you travel, like 1.5 wavelength. That means that you actually have already gotten 180-degree phase change just by the travel itself. But the reflection itself added an extra 180-degree. Therefore, when you come up through here, you are absolutely in phase with 1. So you are constructively interference. And m can be 0 or 1 or 2 or 3 and so on. And condition for destructive is when you say, I actually went integral multiple of the wavelength, and yet when I came out, I got killed. Why? Because when I actually got reflected, I myself had a 180-degree phase change, and one says, oh, you killed me. And you now say, for destructive interference, it is 2t, whatever is t, is m lambda. And so when you're doing it in a lab, you can then say, what is the wavelength where you will get destructive interference? And you can then figure out for the thickness where this will happen. And you will then say, oh, it will happen over here. Whereas if you move the t a little bit further out so the t is larger, oh, then instead of destructive, it will be constructive. So you will see fringes with this air wedge. Are you following? Are you following the flow? Yeah? Yeah. So this, if you read the book, it can be quite confusing. I mean, they are not saying anything wrong, but it's just kind of confusing. But you have to basically look at this diagram with this added t in here in the way I have shown it. Then at least you can appreciate it. Or at least. Okay. And now I downloaded another picture from somewhere, I don't know where. You can download it yourself, where it says no phase change here. There is half wavelength phase change here. You can then work out the way we did just now, all right? And when you now have a, not a air, but sort of like a disk, well, you will see the same thing. You will see these fringes where this is now all red and it's green and yellow and red and so on. And it's very colorful. And it occurs all the time. You have some oil slick that is on your floor. You can also detect those kind of fringes. Or you have an oil slick on your basin, you know. Oh, you can also see this. So this is always there, always happening. And in a way, a strange thing is these optical instruments, these people who do all these telescopes and all kind of lenses and cameras, what they are most irritated by is this. They don't want to have all of this messing up the picture of the beautiful scenery that you have. And so they have to spend a lot of engineering work to compensate and to say, I don't want this, I don't want that, I don't want chromatic aberration, I don't want spherical aberration, I just want a true original picture. So, but it is not for us to try to say, how did you do it? Because I don't even know. I don't even want to know, because it's really very messy in calculation for how to shape it, how to do this and that. Okay, are we fine with this thin film interference? I'm just going according to the book here. Okay, all right. So now we go on. We go on to this thing called Michelson Interferometer. And now there is a reason for this. Why even was such an experiment done or carried out? And what's interesting is that this experiment was carried out in America, whereas in those days, you know, Europe was the center of everything. You have Faraday's, you have Lenz law, and you have Ampere and all that, right? And then we also learn about Huygens Principle. But this is an American experiment done in America and Cleveland at Case Western Reserve, or now it's called Case Western Reserve, but in those days I think it was called Case University or Case College. Anyway, why were people interested in doing this interferometer? Because they were interested in measuring the speed of light. You remember Maxwell was one who then says, gee, I can figure out using Faraday's law, Ampere's law, Coulomb's law, and so he's able to put it mathematically together, and boom, voila, he's discovered that light is a wave. And furthermore, the wave velocity in vacuum is 3 times 10 to the 8. But then very quickly, people began to say, gee, I want to measure it. If you tell me it's about 8, I want to measure it. And there was a competition. There were some people that says, oh, it's not exactly 3. It is 2.99 something. And then somebody else in another lab says, oh, but I can do it better. It is now 2.998 something or other, right? And so there was a big sort of international competition to try to do better and better and better. And one of them was Michelson. But he was interested in more than just measuring the velocity of light, although he got his, I guess, his interest and his expertise came from designing these experiments to measure more accurately. But he was more interested now in the following question. We know that sound wave needs a medium. You know, it's my my drummer boy, and beats the drum, and the drum goes this way and that, this way and that, this way and that. So it compresses the air, decompresses, compresses the air, decompresses. So I have now the sound wave. It is compression, expansion, compression, expansion, and it propagates through the air as a medium. And the question is, light, does it have a medium? And for a while, for many, many years, people after Maxwell says there must be an ether, E-T-H-E-R. I don't know what is the word origin. What does ether mean? Huh? That there's some medium, all right? There must be some medium where the light is able to propagate, because they somehow cannot accept the fact that vacuum light can still propagate. So they want to say there must be a medium. Let's call it ether. Now, if there's a medium like ether, it would make a difference between whether, if I shine light here, whether light is going this way or light is going this way. Because if this is a medium, and let's say the Earth is the one, Earth is going through the medium, so this, we are moving relative to the medium in this direction, whereas this, if the whole medium is moving in this direction, this one will have a different velocity than this one. Are you sort of at least get a sense of why people even think about that? If this is a medium, this whole laboratory where this experiment was held, was designed and done, this whole Cleveland, well, this whole Cleveland is moving sort of like through this medium. And let's say that the medium is here and this whole apparatus is moving against this medium, right, going this direction. Then the light wave velocity, when it is going in this direction, will be different than this. Why? Because this one, it is not moving against the medium, it's moving inside the medium. And so what Michelson, and then we'll find that he had an assistant who is Morley, M-O-R-L-E-Y. So it's also called Michelson-Morley Interferometer. And what they were doing was to say, let us now measure the velocity of light as it now is going through a medium, an ether, and to see whether there's now an interference between this and that. Because if the wave, if the velocity does in fact depend on the medium, then the wavelength of this depends on it, because the frequency is just frequency, it doesn't change. If your wave velocity changes, then the wavelength changes. And if the wavelength changes, there will be an interference between this wave and that wave. Are you understanding the principle I'm trying to explain? If there is indeed a medium like ether, and this whole thing is rushing through the ether is here, and the Earth and the Cleveland as a whole is moving this way, then the wavelength of light that is going this direction will be different versus the wavelength of light that goes perpendicular to it. And therefore, if I now sit over here, I will have, of course, this light got reflected, it came through, and now I observe it, versus this other split beam, and the split beam goes this way and get reflected over here and comes back here, and I want to look for interference. I want to look for any observable interference. And what they did was to say, I put a slab, what they call a beam splitter. I want to split I want to split, not spit. I want to split the beam. I want to split the beam, and therefore this light ray will be reflected here and then be reflected there and comes through. And there's no phase change here. You know, there's no phase change here because this is dense medium, this is light medium. And now when it has been split, the transmitted one will go through, and they put a compensating plate. They put a compensating plate so that now this light will now have to go through this part, which is the same thickness as this. This is the same thickness as this, and it will now go there and get reflected and come back through. And now this one went through this plate, this beam splitter, once, twice, 3 times. You follow it? It went through here once, then it went through here, so the second time, then it went over there and came back here and went through here, so it went through 3 times. This beam, it went through this, so once, then it went through this, so twice, then it came back through here 3 times, and then it got reflected. So both beams went through the same path length, and they had no surprises because the rule for the 180-degree phase shift doesn't apply. This is being reflected from, this is dense medium, this is light medium, so there is no 180-degree phase change. So they look for interference. They looked for interference and they saw none. Now, it took quite a bit of expertise because you want to be absolutely sure that this distance here is the same distance here and so on. So you have to give your, your kudos, right? The number of thumbs up to them that they were able to do it. And furthermore, that when they reported it to their, physical society, that other people say, wow, yes, because they took all of the necessary precautions and all of the necessary, steps to ensure that indeed this is zero interference. But now they could not just simply say, I measured it in, on April, what's the date? November 10th. I measured it on November 10th and I now present the answer. No, they waited and measured it not just November 10th, but December 10th, all through the year, January, February, and so on. Why? Because the Earth is going in an orbit around the sun. So indeed, vacuum is not vacuum, but is ether. Your lab, your instrument, is now going through at different times of the season of the year. And if I find absolutely no interference all through the year, then I know that there is no ether, that the velocity of light remains the same through all. Just simply, it is independent of the ether. All right, are you okay with this? Now, you might say, why is this Michelson-Morley experiment so important? That's because we will come to special relativity in chapter 28. And this Michelson-Morley experiment confirmed for Einstein. Einstein then says, therefore, the velocity of light is an absolute constant. It does not depend on where you are. It does not depend on how fast you are traveling, which direction you're traveling in space. The velocity of light remains 3 or about 3, 2.99 blah, 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 times 10 to the 8 meters per second. We will come to Einstein. So it's because this actually established the basic concept that there is no ether. Okay, so now I want to spend a little time because let's not be stressed out. Let's now learn something about what it means to be a success. Albert A. Michelson was born 1852. you notice that that is much later than James Clerk Maxwell, much later than Faraday. This is now basically the 19th century, close to the 20th century, right? Well, he was awarded. Now, I found this very interesting. He was awarded a special, basically a scholarship, special appointment to the US Naval Academy in 1869. Can somebody do the math for us? In 1869, how old was he? Somebody do the math for me? Yeah, 17. Well, 15, no, 17, right? Well, it could be 17, it could be 16. It depends on which year, what month, right? But what I found interesting is he got this special scholarship to the Naval Academy, but it required the signature of Ulysses S. Grant. I don't know today. Are there scholarships that are given by the president? Are there presidential scholarship that is signed by, President Biden, President whoever's the president? I don't think so today, is it? But anyway, Michelson, at the age of 16 or 17, was awarded an appointment, namely, admission with a scholarship to Naval Academy. And then he graduated in 73, which is about what, 21 years old? That's about the usual age, right? 4 years later. So 4 years later, he graduated, like as if he graduated from City College. And then he spent 2 years at sea, because after all, Naval Academy, you have to be a naval, sailor. And he returned to the Naval Academy in 1875 to become an instructor in physics and chemistry. He got interested in physics and chemistry, but he served in the Navy. What his contribution was, he measured the speed of light in air, because after all, his experiment was on the earth, so it is in air, right? He measured it to be 299,864 plus minus 55, and then he estimated the speed of light in vacuum as 299,940, because he realized that air has a density n equal to 1.0 something or other. So he then says he did a very careful measurement, and then he estimated. All right, that's all part of the, as I said, the international competition to try to get better and better values. And then in 1883, which is what, 31 years old, he accepted a position as professor of physics at Case School of Applied Science in Cleveland, which today is part of Case Western Reserve. Yeah. So he became a professor of physics there and concentrated on developing improved interferometer. And in 1887, at the age of 35 years old, 34, 35 years old, at the age of 35 years old, he and Edward Morley carried out the famous Michelson-Morley experiment, which failed to detect evidence of the existence of the this is a wiki. Luminiferous and ether. Well, I don't know. Lumini means light. Ferrous, I don't know. Anyway, whatever this luminous, but it's ether. It proved that it does not exist, right? Failed to detect the evidence of an ether. So this, for which he was awarded Nobel Prize in Physics in 1907. That is when he was 45 years old. Yeah? But then I was interested. if this is Michelson-Morley experiment, how come it is Michelson that got the Nobel Prize, but not Morley? If you were Morley, would you not cry? I'm asking this, it's a real life issue, you know, because there are many cases where somebody didn't get the Nobel Prize, right? Even though he was part of it, right? Wouldn't you sort of like say, I did part of the experiment myself, you know, I worked on it with you, right? I worked on it, yeah, poor thing, right? So I looked up Edward Morley. Not that I'm a friend or family, you know, whatever. I just looked it up. And there was Edward Morley. I mean, this is the picture from Wikimedia. So I looked him up, and then I found he was born in Newark, New Jersey. Now that comes, oh, Calvin, yes, right. I mean, there are many such, it's not a rare thing that there are people who have been left out, and you do wonder how come he was left out. And my question rather is, how did that person feel if he was left out? And I can tell you some stories in modern days of examples where someone was left out of a Nobel Prize, but that someone was not bitter. The important thing is you cannot be bitter, because if you're bitter, that bitterness is a grudge inside you that really becomes very smelly. So anyway, so here is Morley. He was born in Newark, New Jersey, which is not far from us. Both parents were of early colonial ancestry and of purely British origin. During his childhood, he suffered much from ill health and was therefore educated by his father at home until the age of 19. This is what today people call it homeschooling, right? And in fact, today there are some parents, because of all the pandemic, they don't want their kids to go to school, so they want to teach them at home. But this now is the father who actually taught the son until the age of 19. And then in 1857, which is how many years old? 19 years old, he entered Williams College, which is a pretty famous college, right? It's not quite Ivy League, but it is next to the Ivy League, yeah? William College. His father's alma mater, and he received his AB in 1860 at the age of 22. And his master's degree in 1863, which is 25 years old. I mean, so this is sort of like, it's a normal career. You go through college. Presumably he did well. I don't know what grade he got from 207, 208, 204, or whatever. And he received his bachelor's and master's. But upon advice of his parents, he entered theological seminary. Well, he's an obedient kid, you know. The father taught him until the age of 19, and he went to the father's alma mater. And then when the father says, you should go to the theological seminary, so he did, finishing in 1864. That means he actually, you know, studied there. And in 1868, became a pastor. But he was also appointed professor of chemistry at Case Western Reserve. And what he did was he collaborated with Michelson for several years around 1887. Because when he became professor of chemistry, somehow he got in touch, or was, got acquainted with Michelson, because Michelson is in physics. Now that shows something, and I just want to advise people. You may be trained in biomedical, on particular field of biomedical. You should when you become a professional, when you're working in whichever environment, keep an eye out for other colleagues in other departments. You could be in biochemistry, or it could be in biophysics. Because by opening your eyes, you can then maybe be led to a certain new direction which you never thought of before. You understand what I'm trying to say? It's a good advice, and I have other examples of it involving our own City College graduate, Arno Penzias, who is a City College graduate, but we will leave that until maybe at the end of this course. He was a graduate of City College and then went to Columbia and then got a PhD under a very famous professor, but then did not get the kind of position that he wanted, but he kept his ears open. That's what Morley did. He kept his ears open, and he was a professor of chemistry. And you can say, hey, you're a professor of chemistry, just do all of your chemistry experiments. And he's also known for some, I did not download all of the things he did in chemistry, but he was a good professor of chemistry. He did things in chemistry, but he also had this, let's say, outreach. He had this contact with Michelson, and Michelson was saying, "Oh, I'm doing this experiment, but it is very hard to be sure that everything is clean, everything is precise, and with this interference interferometer." And Morley now says, "Yes, I will help." And now I want to point out something. How old was Morley when he was helping Michelson? I need somebody to do the math for me. How old was Michelson? Was Morley when he collaborated with Michelson for the famous Michelson-Morley Interferometer? How old was he? How old was he? 49. How old was Michelson? Michelson was just, 30 something, right? It's 87, so what is it, 35? Yeah? No, 35, isn't it? 87 minus 52 is 35. So Morley is older. He was, what was it now? He just did that. 49. He was about 50 years old. So this is one where he is saying, hey, you young man, you have this bright idea. Oh, I'm willing and able to help you. And he contributed many things about the lens, about how to do the chemical aspects of the lens, because you want to be sure that you have you don't have these interference, due to the fact that your lens itself is causing you thin film interference. So Morley was an older person helping with the younger person, but then we all know that the world recognized Michelson, and it's now called even though it's now called the Michelson-Morley Interferometer, it was Michelson who got the Nobel Prize. But Morley got a lot of award recognition from the Chemical Society. And he was also made a fellow of the Royal Society in England, because after all, he is a British. His family came from Britain. So he got all the honors except for this big one. But now we want to come to diffraction, because, there's still 10 more minutes. Because I remember the last time somebody was asking, I don't remember who it was, but somebody asked, if I have a light coming through this, this slit here, if I have a light coming this slit, how come it started bending? Right? Didn't somebody ask that question last time? Does anybody remember? Oh, you, yes. how come the light would bend? Well, then at that time I says, Huygens Principle. And now I want to spend a little time because it is good. It's not difficult to understand Huygens Principle. Huygens Principle says that this light that came is a sort of a wavefront. It's the beam of light from, let's say, the sun or from the star. And when it now comes through here, Huygens says each point of the wavefront is itself a source of a wave. And therefore, when now this wave from here comes out, there will be a wave come from this point, and there's a wave from point 2, there's a wave from point 3, there's a wave from point 4, and you can see that over here it is sort of the same parallel, but over here it now is bent. Why? Because each point is a source of wave. Therefore, the light can indeed propagate in this direction. You see now the picture? All you have to say is, I believe in this principle called Huygens Principle. And immediately you say, yeah, that's why this light. It should have been just straight all the way in, but in fact it can turn because each point along your wavefront is a source of a new wave, secondary wave. All right, are you comfortable with this concept? Okay, now I have downloaded a picture of from Wikipedia. Wikipedia is trustworthy, so we don't have to worry because these days there are many websites that you're not sure that there is legitimate. And it shows you have a plane wave, and now this plane wave is blocked over here except through this little slit. And now when it went through this little slit, what you find is spherical waves coming out. So this is then a manifestation of what is called Huygens Principle. And I will download a picture also of Christian Huygens. He's proposed this at age 49, sort of like Morley helping out with the Michelson-Morley. And he proposed that every point to which a luminous disturbance reaches becomes a source of spherical wave. The sum of these secondary waves determines the form of the wave at any subsequent time. So here you have just a spherical wave from this small slit down here. Well, I downloaded from the internet the actual, let's say, picture. If I have a plane wave, and if you now say each point is the source of new wave, secondary wave, so A is the source of this wave, and B is the source of this wave, C is the source of this wave, then you can see that indeed the new wavefront is exactly parallel to this, right? It's kind of easy to understand. But now supposing the wavefront itself is spherical because it came from a star and the wave is a spherical wave. But now each point on this spherical wavefront is itself a spherical wave. And this point is itself a spherical wave. This one is itself a spherical wave. Of course, then the new wavefront is a spherical wave. So therefore, this totally is consistent with our intuition. The only thing is that the new consequence of it is that we get diffraction. Why? We get the, as we showed earlier, as we showed over here, you have light coming here, you can have the light ray bending beyond the ones that were straight through. There are some light that actually bent. Okay, so now we have this, and now we can also relate something to the velocity. I have my plane wave, it has a certain velocity v, and now each one is the source of secondary wave. So this is a new wavefront, and in a time delta t, this new wavefront will be at a distance which is v delta t. So again, that's very easy. It is in sync with our notion of what is a wavefront, and likewise with a spherical wavefront. This will again be whatever is the velocity delta t. Okay. And now the book has this, but I like the one from the Wikipedia. And now we can now see what happens. If there has been no diffraction, then I have the slit, a very narrow slit, then the light would fall only on here, and you will have only one image of the slit directly. But because of diffraction, you see, this is not a double slit experiment. This is now a single slit. I make the single slit, and it is a very narrow little single slit. And now I shine light on the single slit. Ooh, I get again fringes. But these are now diffraction fringes, not Young's double slit experiment fringes. Young's double slit experiment, the D there is the width, the distance between the two slits. Now I have just one single slit, a narrow slit, and yet I get a diffraction. This is called diffraction. And you can now figure out. How do you figure out? You say, I know that I would like to now know what is the phase difference between the light that came this way versus the light that came this way. Well, I can now magnify it, and I now draw it out here. And what I find is that if I take the wave that came from 1, wave 2, wave that came from 3, 4, and 5, that the wave that came from 5 has a longer path length than the guy from 1 to reach my screen opposite over here. And if this longer wavelength is indeed exactly one wavelength, it will be constructive. But if this is indeed half a wavelength, it will be destructive. All right? So we now have a condition. The condition is for there to be a dark fringe. I want there to be a dark fringe. I want this to be half a wavelength so that there will be destructive interference. And sine theta, the angle, is m lambda over w, because that's the trigonometry. This angle being theta, then sine theta is m lambda over w. W being the width of the slit. It's a tiny slit. It's the width of the slit. And if you now say, in the middle, of course, there's no destructive interference. It's totally bright. And the destructive interference will occur over here. And you will now have, this is the formula. The intensity is over here. This will get less intense, and less intense. Well, okay, I think this is about the time. Now, as I said, I will see what the grader does by later, and if he has not, I will then spend tomorrow looking over each one. All right? Any questions or comments? Okay, so we'll see each other again on Monday. By the way, I have now put up homework 27 online, Wiley Plus. And I have also put up special relativity A, I mean homework 28A, namely the first part of special relativity involving time dilation and length contraction, up also, because the test on November 22nd will be for whatever we have been able to cover today and on Monday. Okay, so I just want to warn you that, or tell you that it should be up on Wiley Plus for homework 27 and home 28A. Okay, any questions or comments?
Professor?
Yes.
So you're saying that 28, only half of it will be included on the exam?
Yeah, that's right. That's why I put down homework 28A for just that half, which is the first two concepts.
Just 28 point, up to 28.2, right?
I don't know whether it's 28.2 or whatever, but
Do we get to time dilation?
time dilation and Lorenz contraction, the two concepts, they are related. Time dilation and Lorenz contraction. Yeah.
Okay.
Okay.
Perfect. Uh, um, Professor, one more question. Will you ever have office hours on campus, or
No,
I can't?
no, I will not. I will not have any office hours on campus. Sorry.
Okay.
You
Then
can
I'll just.
email me. Yeah, you can email me with whatever issues, and I will spend time to answer them. All right.
Could we ever hop on a Zoom meeting just to show you, like on the iPad, because it's very hard through email sometimes?
Well, I would rather, because once I start that, then you have 70 people all wanting to have their own time, and then I don't have the time.
Okay, no worries. I'll just send an email. All right.
Yeah, I know,
I'll be
right.
concise. Thank you.
But whatever issue you tell me, and I will do my the best to try to explain and to basically comfort you. Okay.
Thank you, Professor.
Okay. All right.
Bye, Professor. Thank you.
Yeah. Okay. Have a good weekend. Stay safe. Bye. Same to you. Right. Okay. I will log off. Bye.